This composition and biomechanical study is seventh in the series and focuses on traffic mobility. Traffic flow occurrences resulting in phantom traffic jams, observing the kinetic flow disturbances, advanced properties of jamitones in three-lane unidirectional system. The location, Crown N1 Highway Interchange, Johannesburg, Gauteng. The date, 13th of February to 4th of March 2010. Time, peak hour, 7 to 9 in the morning and 1600 hours to 1800 hours. Speed, tracking vehicle behavior, recording speed variations, jamitone formations, number of vehicles entering and exiting marked areas, or increasing and decreasing vehicle densities, grouping and selective regrouping. A series of 5 cameras installed in area common to jamitone formation, road uniform, straight road, and weather sunny with a clear view. This is a graphic representation of Crown Interchange, west, south, east leading to N1 North. A study done on various traffic congestions that are going to be transformed into sound. A jamitone is referred to as a traffic congestion that is in motion without stopping. Vehicles enter the congestion at a lower speed and leave at a higher speed. The time taken to exit a jamitone depends on the speed and the amount of vehicles entering it. In the following 3 video clips, which illustrate jamitone simulation at specific positions in circular paths, as vehicles increase due to braking, vehicle density increases. You will observe in the first video clip 14 vehicles at 120 seconds. The second one, 18 vehicles at 120 seconds. And the third one, 22 vehicles at 120 seconds. The use of mathematical equations that model traffic are similar to the equations discussed in 2022 regarding fluid flow. The Vaslov-Fokker-Planck multilane model for analytical purposes suggested a multi-lane traffic flow model on a uniform highway. The equations include non-local and time-delayed braking, acceleration terms with rates depending on the densities of relative speeds. The braking terms include lane change probabilities and generalizations thereof. All drivers behave according to the same laws. The considered traffic models predict a uniform traffic flow at low traffic densities. However, above a critical threshold density, the flow becomes unstable and disturbances amplify. This phenomenon is typically addressed as a model for jamitones that arise in the absence of any obstacles. The instabilities are observed to grow into traveling waves, which are local peaks of high traffic density. Although the average traffic density is still moderate, for instance, highway is not fully congested, vehicles are forced to brake when they run into such waves. An analogy to other traveling waves, so-called solitones. A solitone is a self-reinforcing solitary wave, a wave packet or pulse that maintains its shape while it travels at a constant speed. This research is based on observations. The considered traffic models are similar to the equations that describe detonation waves produced by explosions. In the language of detonation theory, such traffic roll waves are very similar to roll waves in shallow water flows. A central result is that sharp shocks may always face towards the incoming vehicle. It can be proved that jamitones always travel slower than the individual vehicles. Hence, vehicles run into a sharp and sudden increase in density, which forces each vehicle to brake very suddenly. Then vehicles accelerate again out of the jamitone. Analysis shows that the jamitones are stable structures. They can only vanish by strong smoothing effects, extremely cautious drivers, or lowering of density, a widening road, for instance. While one jamitone does not delay the travel time of individual vehicles significantly, vehicles travel through a jamitone very quickly. A sharp jump in vehicle density is a potential hotspot for accidents. Streamwise vehicle velocity profile similar to liquid flow. You can see from the left side to the right the increase in speed. Vehicles go between 60 kilometers and 120 kilometers an hour. Number two is high density. As density increases with vehicles by the peak of the wave. The first video clip shows low density as density decreases with vehicles by the peak of the wave. Number 2 is high density, as density increases with vehicles by the peak of the wave. Vehicles traveling between speeds of 60 to 72 kilometers an hour were least likely to exit the Jamestown formation first, whereas vehicles which were traveling with speeds between 30 to 55 kilometers an hour were able to exit the Jamestown at speeds between 50 to 25 kilometers an hour. Thus, the speed entering and exiting a Jamestown can be attributed braking and acceleration terms. Vehicles traveling between 60 to 72 kilometers an hour were most likely to enter the Jamestown before the vehicles which were traveling with speeds between 30 to 55 kilometers an hour. This diagram is showing potential Jamestown formations at various traveling speeds. The diagram shows 9 recorded observations which I chose due to the unique audio transcription. What I observed was that on day 3, 17, 6 and 13, this included various groups presenting moderate to high densities in kinetic flow disturbances, which are most prominent. The analysis showed a variety of phantom traffic jams that were of longer or shorter duration, located at various points, areas in the mapped location, showing a slow flow of vehicles through the Jamestown. In the audio work, I sketch to the listener the chaotic nature of a hindered, unstable flow. In day 2, the 7 traffic jams recorded in one day had similar properties, allowing for moderate kinetic flow through them. Focusing attention to speed variations and analyzing vehicle speeds on entering and leaving the jams. The only way one could make sense of the situation to produce an audio composition that does justice to the 7 congestion formations was to choose 2 groups of vehicles that represented fragility in the system. The behavior of vehicles entering or leaving the nozzle had slightly different or similar speed variations. On day 19 to 20, 14, 17, 3, 14 and 17, the Jamestowns having a variety of almost similar densities that show a strong kinetic flow. The Vlasov-Fokker-Planck multi-lane traffic flow model contains the lifespan of various vehicle densities. In other words, the number of vehicles per unit length or road entering and leaving a congestion, the propagation of non-linear features of detonation waves that would lead to the formation of jamitones. This application is also used in conditions of various velocities, time duration relationships examining free flow, synchronized equilibria, and congested flow, moving jams, and the build-up to various densities. The higher the vehicle density, the higher the probability of various degrees of congestion. Vehicles were placed in various speed category groups, in other words. Group 1 was from 20 to 40 kilometers an hour. Group 2 was from 40 to 60 kilometers an hour. Group 3 was from 60 to 80 kilometers an hour. Group 4 was from 80 to 100 kilometers an hour, and Group 5 was from 0 to 20 kilometers an hour. The equations used in Vaslov-Fokker-Planck multi-lane traffic flow model that allowed calculations to take place in the fluctuation of vehicle density in a free flow system between day 2 to 20. The momentum equation, the lane change probability equation, equation determining braking, and the diffusion coefficient. The following time domain diagrams show a variety of jamitone formations at 120 seconds. Displacement, velocities, and acceleration are time domain measurements, meaning their amplitudes are plotted versus time. Data sample signals contain useful information such as noise and harmonic content that are difficult or impossible to detect when the amplitudes are plotted in the time domain. Displacement, velocity, and acceleration amplitudes are expressed in the frequency domain, that is, amplitude versus frequency. Abnormalities in the form of high amplitudes at certain frequencies become visible, narrowed down, or identified based on variations in amplitude and certain frequencies. To note, a time domain plot is referred to as a waveform, and a frequency domain plot is referred to as a spectrum. A process often referred to as the spectrum analysis or Fourier analysis. A frequency spectrum plotted from day 19 and 20 results. A frequency spectrum plotted from day 3 and 17 results. To understand fast Fourier transforms, it is helpful to first understand the underlying process known as the discrete Fourier transform, or DFT. A discrete Fourier transform tests the time domain waveform to discrete or individual frequencies based on the length of the signal n. The number of frequencies or data samples required is equal to the signal length squared. Even for small signals, this can take significant time and computing power. To make the Fourier transform faster and more efficient, a method known as the fast Fourier transform is used. To summarize fast Fourier transform, it's a highly optimized implementation which convert discrete signals from the time domain to the frequency domain. And computations provide information about the frequency content, phase, and other properties of the signal. In signal processing, this forms the basis of frequency domain analysis, spectral analysis in other words, and is used for signal filtering, also allowing for simultaneous analysis in time and frequency domains. The underlying mathematics of this assumption eliminates redundant calculations and those that have no value. It's important to note that the sampling rate must be greater than the highest frequency component of the signal to ensure the sample data accurately represents the input signal, according to the Nyquist sampling theorem. Creating frequency bins allowed for more efficient spectral analyzing possibilities to take place for each frequency presented. The fast Fourier transformation made the collection and organizing the storage of data more manageable, eliminating unwanted frequencies, placing them in labeled frequency bins that could be used in transitions between moments or with frequencies of similar properties, for example, similar frequencies, date, and time of sampling data collected. The composition consists of various Jamison formations. It is made up of 9 tracks with a duration between 1 and 2 minutes.